This is a video on how to set up and tune a Viper 200 DC servo drive made by Larkin Automation. I'm Larry Kenny. So the Viper 200 is a step-in direction drive. So it closes the loop on the motor using the encoder and the motor power, and the motor is driven clockwise or counterclockwise by a step-in direction input on this connector here. So this is a Viper 200, and the 250 shares the same layout, except it's a higher power version. So they're the same drive pretty much, other than the power rating. So on the drive, this side here is isolated from this side. This is the control side, this is the power side. And there's opto-isolators that isolate the two sides. So your on the control side, you have your encoder, and you have your 12 to 20 volt DC power source here. You supply it with your step-in direction connector, your fault and error output connector, and your RS-232 programming connector here. Then on the power side, you have your the motor connects on these two terminals here. The brush connects to the brush DC servo, and this is where your power comes in. Now, so the drive, the power should be between 65 to 160 volts, and on this drive, 160 max, because the drive will give an over voltage fault at 180. If you're decelerating and it hits 180, it'll trip out and show a fault. It'll disable itself. The motor connection connects here by screw terminals. It's important that you never have bad connections on these terminals, because if you ever powered it up and had a loose motor wire, the loose wire will cause an arcing, because a motor is an inductive device. It's coils of wire, and just like a spark plug on your car, if you have a gap and an inductor, the spark will jump between the gap as it's disconnected, and it'll generate a high voltage. So you can get a couple thousand volts by accidentally sparking the wires between the motor and the drive, and that'll blow the MOSFETs under the drive. So very important, you always have a very secure connection to your motor terminals and your power terminals too. The encoder, you're best to use a differential encoder. You've got an A channel, a B channel, and 2 wires for the A, 2 wires for the B, positive and a negative, and they go into this connector, and it's in the manual how to connect them up. Use twisted pair wires if you can. They're the best for rejecting noise. You don't even need to have shielded wire. Twisted pair is fine. I use a twisted pair stranded wire, flexible stranded wire on my machines I build. And but a single-ended encoder is just a remedy to have a noisy machine that loses steps. You want to get the differential, and the US digital encoders are probably the best you can get for the price. Don't use those little plastic encoders, those little toy encoders that push on the shafting. They're about 30 bucks. They're just junk. They're just for toy cars and stuff like that. So don't use those, even though some people recommend them. No, they're not reliable. We have many cases where machines just kept losing position, and they're no good. Anyway, so we're going to connect the drive up here. Now on the drive, you've also got on the Viper. This is the 200H model. It's after the 200F. So here, down here, I've got a green LED. That's the power LED. It comes on when there's power here. This is the fault LED. It flashes the code, the fault code, so it can it goes from 2 flashes to up to 13 on this drive. Well, 13 is a special fault. But and then over here there's a little yellow LED, and all this little LED is telling you is that when it's flashing, it means that this side is communicating with this side. Because there's 2 microprocessors on this board. There's the DSP30 here, 30F DSP processor, and then I have a current sense processor. I'm using a little pick to measure the current here, and it transmits over to this processor through these optocouplers. So all the little flashing LED is telling you that these 2 are communicating. Anyway, so I've got to connect it up here. Now I use this quick connects when I'm testing a drive, because I do a lot of testing of drives. So instead of running wires, I put these in here. So here I've got a SEM DC servo over here with an encoder on the end. So this is a 140 volt servo. I use this for testing all my motors and drives, testing all my drives, I mean. Okay, so first of all, what we're going to do is, before we even connect power here, we're going to test the encoder on the motor. Okay. All right. Part 2. Okay, what we're going to do here is, before connecting power to this side of the drive, we can test the encoder on this side of the drive and make sure the encoder is connected properly using ViperTune. Now you get ViperTune, you download it off my site, viperservo.com. And so what we're going to do is we're going to connect the encoder here. This is the encoder for this motor. We're going to connect the programming cable, the 5-pin programming cable, to the connector. And then I'm going to power it up with a 12 volt DC. And you see it always flashes when you first power it up. And it's flashing an error code of 4. 1, 2, 3, 4. And 4 flashes means under current, under voltage, okay? And that's because there's no voltage on the side of the drive yet. So it's saying that there's no it doesn't see any voltage over here. So what we're going to do is, here's the ViperTune, hit connect. Now on these drives it's set up as a baud rate of 38400, which is the high-speed baud rate. On my older drives I use 9600. So this is the terminal screen that it does all the commands through. And this is an RS-232 interface. So when I hit connect, it sends a command to the drive to see if it's there, and it sends a version command, just the letter V, to the drive, and the drive comes back with V version 4.2. It's a V200H revision B. So if I just hit like another V, I keep getting that. Now this is the little send terminal, so you can put a letter in there and send. But this is all done automatically by this if you want. But you can enter commands in here too. So I'm talking to the drive now. So we can hit read drive, and it's going to read the parameters that are in the drive. So first of all, we've got the gain parameters, the PID, proportional integral gain, and the derivative, and then the feed forward and the loop time. These are grouped like they're fairly important parameters. Then the next one is the integral gain, the step multiplier, balance, hysteresis, and then up here we've got the current. So we're going to read the drive, and so what it does is it sends a few commands to the drive, and it comes back with the parameters, and the parameters are there. But anyway, so the proportional gain is 400, derivative gain is 1,000. It's set with a step multiplier of 1, and integral gain is set to 0. That's good for starting. What hysteresis is it's like the MOSFETs. The MOSFETs are not linear right off the bat of the PWM, so it gives it a little head start on the PWM. This is a PWM setting. The drive over here, you can also, so what it has is it has a current setting inside the drive. That's not 20 amps, that's a setting of 20 on the analog to digital converter inside the chip. Okay, so it said it read it as a V200H. All right, this is a preliminary version of my latest one here. So, okay, so we're able to read the parameters from the drive just by using the read parameter. Now, this is down here is the oscilloscope or the display scope. It doesn't show anything unless you hit start. So we'll hit start and it starts to scan. Now, if I move the motor, you can see the encoder is going plus and minus. It's working perfectly. So I'm able to see the green line is the encoder. So what I'll do is I'll hit, instead of encoder and step, yeah, it's encoder and step. Okay, so the green is the encoder, and the step is, there's no step pulse coming in, so it's seeing 0 in the step. So the important thing is to be able to read the encoder plus and minus. So if I move it, let's say I move the motor this much, 60 counts this much, and I come back to 0, and I should go the other way 60 counts. So that's in the positive, that's in the negative. So as long as you can read that reliably, and your 0 always comes back to the same spot where you were on the motor, you know you're reading your encoder. Now if you just give it a pulse and it only moves a couple, and it doesn't come back, there's something wrong. You should be able to go fully one way and fully another way and come back to your 0. That tells you your encoder is working. So it's important to make sure your encoder is working before you go to the next stages, which is to connect up the main power. Because if the encoder isn't working and you power this up, the motor is just going to go, it's going to run away, or it's going to do something very bad. You know, it's not good for it. It could damage the drive too. A sudden high current spikes caused by a bad encoder. So first of all, just check your encoder. All right. Okay, so I stop scan. You can see as this is scanning, it's sending the M command, which is repeated to get back the data from the drive, to tell it the step and the encoder position, and then it calculates the error here. All right. So I'm just going to unpower this, the 12 volt. Okay. So I'm also going to put a little tester. All it is 2 LEDs. I'm going to put that on the error out, and that's where if you want to connect your errors to a remote, like the wire, on this here, the sender is plus 5 volts. The terminal on the other side is a remote flash that you can put to the front of a control cabinet. So you would use the plus 5 and a remote flash going off. You need a resistor in series too with that, but you can gang all 3 drives to the same error fault light and put that in the front of your cabinet. Then on this side here, you've got a fault output that goes back to your controller to stop the controller if the drive faults. So this line here pulls low if it gets a fault. Now the 12 volt power comes in here, and one of them is the ground, negative, and the positive. The negative can be used with this one. So if you have a breakout board, you can connect your common negative to the same incoming 12-volt common negative as this. So when it goes pulling down, it's pulling down in relative to the power here. So we're going to put this on here, and you'll see whenever I power it up, the yellow light flashes, and then it goes into fault because it's got a 4-code flash. It's saying it's low voltage. Alright, so what I'm going to do is I'm going to take that off. I'm going to add these test connectors that I use for testing drives. I don't put wires in them, I already have connectors on them, so I put these two connectors in here. They have I've tested thousands of drives with these connectors, literally. Okay, so now I'm going to connect the motor into this terminal here, and then I'm going to connect the power. Now here I have a 90-volt power supply, so it's not turned on yet though. I'm going to plug it in here, and then I can turn either one of these on first. I could turn this side on first or this side on first. Depending on your system, you'll have to see. So what I'm going to do is I'm going to put the 12-volt side on first. Now you can see I can turn the motor here, but as I turn it on, it locks. Now the motor is locked. The motor cannot turn because the drive is locking it. The drive is seeing the encoder is telling the drive that I'm moving it this way, and the CPU and the PID loop is pushing it back, so it's holding it. Now it's a little soft here, as you can see, but that's because it isn't fully tuned. Also because this power supply it doesn't have enough current to really control this motor very solidly. If you don't have a power supply that can output all the current the motor needs, you'll never be able to really tune it to its really hard, you can't really do hard tuning on it because it's up to the power supply to be able to control that motor. And if it doesn't have the current, then it can't really fully control that motor. So if I go over here now, I'm connected again. I'll just hit I'll hit the scope, and the program is very good to stay in sync. You don't lose connection very often unless you're using like a USB to serial converter, and they can be a bit problems. So you can see as I'm moving this, I got a little bit of play here. Okay, the error can go plus or minus 14, and what I'm feeling is there's very little between these two. What I mean is, it's not even trying. There's like a dead zone here. Now that would be the hysteresis command that will take care of a dead zone in your drive. So, but first of all, we're going to start the exerciser. Okay, so I'm going to stop this, and I'm going to change. And if I could start exerciser, actually it tripped. Okay, so it tripped, and it's giving 1, 2, 3, 4, 5, 6. 6 means current trip, exceeded motor current. So when it started to oscillate, it exceeded the current that the drive is currently set to. Well, what we'll do is we'll just slow it down a little bit here, send the velocity to 4, and I'll do reset drive. If I hit enable drive, okay, I'm going to update. So now I just did I changed the velocity to 3, and I did an update. Now if you see it, if I change it to 4 and do update, it goes fast. But 3 will keep the current without tripping on this here. Okay, so, and I can also change the amplitude of the is how far back and forth the exerciser goes. You'll see. Okay, I'm going to increase the amplitude. Okay, the smaller the amplitude, the faster it oscillates. Okay, so I'm going to do update, and I'll do enable drive. Okay, so now if we start to scan here, I'm going to change the display here. Now what the green is where the drive should be, and what the blue, that's the step signal. I'm also going to bring this up here closer, so you're getting we're changing the sweep time on the scope here by adjusting this. Okay, so you can see it's fairly loose. Now, okay, I'm going to put it there. There's a good one here. Okay, so what we're going to do, so I'm using the scope to display the step signal. Now it's doing an internal step signal from inside the exerciser here. So the exerciser is outputting a step signal inside the DSP processor here. Okay, so it was software, but you can use this for tuning. Now I'm going to increase the proportional gain here. What you do to tune it is I'm going to increase the proportional, but I'm also going to increase the derivative at the same time, and I'll do update drive, and you're going to see it's a little bit tighter. See, there's less error. Okay, and then there's a few others here to try. You got your feed forward, and you got your loop time. So we're going to try a different loop time here. The loop time can be between 1 to 15. Now 1 is the slowest, 15 is the fastest. 15 is around 3,000 to 4,000 corrections per second, and 1 is about 1,000 corrections per second. So we're going to increase the loop time here. We're just going to see if it does anything. Now what loop time also does, though, is it also speeds up the exerciser. So I'm going to slow it down here. Okay. I'm just going to stop the exerciser. Now you can see it vibrating here. It's not very stable right now. So if we increase the derivative, you're going to see that it's going to reduce that effect. I'm going to increase it quite a bit and do update. That's pretty unstable right now. I'm going to change the loop time back to 4. Okay. Okay. No, that's unstable. Now part of it can be Okay, start again. Okay, so I decreased the, so it's fairly stable now. The settling time is pretty good. Now I did a few things here. What I did was decrease the proportional gain to a number that I was happy with, because if I go too high on that, then it gets unstable. So if I was to change it back, let's say to 11 up to close to 1200, it's quite unstable here. It's ringing, but it seems to like a lower value there. See, it settles pretty fast. I'm also going to increase the derivative here even higher. Okay, see, fairly fast settling time on it there. Now that's a pretty big flywheel. I purposely have a heavy flywheel, and that power supply is not really got enough current to really control that motor. So that's two reasons why it isn't a bit tighter. Okay. Now, one of the things here is the hysteresis was at 20. I'm going to change that here. Okay. Now, if I update it here, when it was at 20, I'll just show you. I had a error, a looseness in a dead zone. Okay, of about this much, and that is about +4 counts to -5 counts. So it's about 10 counts of dead zone. Okay, and I'm not using any force at all. It's just a dead zone. Now if I change this number to 30, you got to be careful with this number. You don't want to go too high. I'm going to update. Now the dead zone is about half. The dead zone is about -1 to -2 to +1, which is 3 counts. You got to be careful though, because what it is it's the dead zone between turning on the upper MOSFETs, and the lower MOSFETs, and you have to have a little bit of a dead zone there, or the drive will continuously dither. So let's say we increase this to 35, and we update. Now I've got almost no dead zone there now. 1 count of dead zone, okay? And that's pretty good. Depending on the motor, depending on the drives, and depending on the power supply, you can adjust the dead zone. You don't want to go too high here, because then you're going to make the poor drive, the MOSFETs both trying to come on never turning off. Okay, so I'm going to hit update. Now you can see I set it to 40, and it's sitting here vibrating between 2 counts. Now you'll see when I set it back to 30 and I do update, it stopped. Okay, so this number here is the dead zone in the drive. Hysteresis means it's a stiction. You mean it doesn't want to go until you give it some more, and then it comes back. It's like something that doesn't move smoothly. It's like a lack of friction. Now balance, balance you would use if, let's say you had a z-axis on a machine where you have a weight always forcing one direction. So let's say I was always pulling this direction on the motor. Balance you can adjust to give it so the resting PWM isn't 0, it's up a bit. So what it does is with a balance of 0, if I always had a weight one direction, you're always going to have an error on one side more than the other. But the balance would, you can adjust it a little bit here, a little bit at a time, maybe 5 counts at a time, until you're sitting with 0 error. What it does is it helps the PWM. It gives it a little more. PWM means pulse width modulation, and that's the power coming out of the drive to the motor. So it gives the PWM a bit of a bias one way, so it's always that way to counterbalance the weight. Okay, so that's what balance is. All right, so now I'm going to trip the drive here just by giving it some current. There, I tripped the drive. It's actually set at a fairly low current right now. So it's flashing here. 1, 1, 2, 3, 4, 5, 6. Now it flashed as a current warning. 5 is current trip I meant. Okay. So anyway, we're going to reset the drive again. I can reset it just by this enable command on this here, right here. Okay. And now if I just give it a little bit of fault, now if I give it a big turn, and let me see. Now that was 5 flashes, and because I gave it a big turn, so it sees that the big before the current tripped, it tripped because I went really far. So it says encoder trip, so that it now here is the encoder trip. I'm just going to stop this. Okay, so these parameters are the warning. At 200 counts of error, it'll flash 2 flashes, but at 2,000 counts, it'll do a hard trip. Now this number should be less. Normally you would run that about 500 or something. That would trip the drive if the encoder counts exceeds this number. Okay, this number, it would just flash 2 flashes, encoder warning. Okay. But it'll also output a fault. I think it will. Anyway, so pause. Okay. Some of these numbers you don't. Some of these numbers you don't play with, like PWM clip. Don't play with these numbers. These are numbers that you shouldn't have to touch. This is actually the PWM limit that the internal software uses. If it exceeds that, you don't want. It could damage the drive, so you don't want to mess with that. Now, I'm going to enable the drive again. Okay. Now, let's say we want to set the current here. So, to make sure I had the right drive, I clicked the right current table for this drive. I clicked on the Viper 200H. Okay. And because each one of these have a different current table, so you want to make sure that you've got the right one selected here. Even if it didn't find it automatically, you can just click on it here to make sure you got the right one. So this drive can be set anywhere between 4 amps and 30 amps. So let's say we're going to set the drive for 8 amps. Okay. So when I did that, this is actually a number that goes into the ADC analog to digital converter inside the drive. So this number, this is your current in amps, and this is a random number that it puts in the drive. So you don't change the number here. So let's say we go to 9. This number will be, what it's doing is comparing an analog value from what it read through the current sense chip to the ADC here. So we're going to set it at 7 amps, let's say. Okay, so what you do is then you do update drive. When you move a change, so it changed that. It sent, you can see the command it sent was A20. So A is the parameter for inside the drive for changing the current, and it put a 20 after it. Okay, so now let's say you want to save the parameters. You would do burn to drive. Okay, burn to drive sends a command to tell it to burn it into its flash. It sends it in the terminal here. Okay, so now we got harder to turn a little bit. Okay, I'm gonna change this here to 10 amps. Update drive. Okay, well, now it's harder to turn. But what's happening here is this power supply is only rated at about 6 amps, so it really is loading the power supply down. So if I hit the scan here, here we got the voltage. Okay, over here, these bars, this is the amps, and this is the voltage. So as I drop it down, as I load it up, you can see that voltage drop down to 84 volts, 79 volts. All right, but it's holding that current. you can see here now with the tuning, it's fairly okay. The error is fairly low. It's holding fairly tight. So the step signal is comes in, and the encoder signal is following it fairly closely, and the error is fairly low. Okay, so I'm going to stop that. Stop exerciser. Okay, so so now this is a little pulse generator here. This is what I use for testing. It's just a pulse generator. So I'm going to put it simulates a your breakout board and your CPU. So just by here's the okay. There's my speed, and that's the direction. Okay. All it is a 555 timer, and it just outputs to the step and direction. So what we ended up here was, for this 90 volts, and a gain of a P value of 800, a D value of around 3000. I didn't play with the integral, but it you can add a bit of that at the end. It's something you got to be careful with, because it can make the drive unstable. But let's say we can update it here to 4. Okay, let's try this. See, I'm disturbing the motor and seeing how fast it settles, okay? So what the integral is it kind of fights you. When it sees you move, it gradually over time fights back. And then, so if I pull it this way, it gradually over time fights the other way. It accumulates over time. Okay. So this is how you tune it. You basically you increase your settings a bit at a time. You update to the drive. You test your motor, your disturbance, and you see how it reacts. And then so you're mostly working with your P, your D, your loop time, and you can do the hysteresis one right at the start to tune it to get rid of your the play in the motor, the backlash. It's not backlash, it's kind of an electronic backlash, a dead zone. But you need a little bit of a dead zone, though, if you want your system not to sit and squeal or dither on one spot. The main reason for dithering, though, is when you have a encoder resolution that's too low. That's the main reason. The higher your encoder resolution, the less chance of dithering. Because what happens is, if the drive has to give it one count of correction and it moves it too far, then your PWM resolution is a lot to do with dithering. If your resolution is fairly coarse, and one change in PWM resolution makes the motor move, well then that causes it to come back the other way. So this drive has a 1024 count PWM, which is fairly high resolution for a DC servo, and it is a very stable drive. All right, so that's going to be now. Oh yeah, so hit the stop on this. Now what this is, this over here is, this is a save buffer. So let's say you have all your parameters here, and this basically is just a temporary area to save parameters before it gets saved to the drive. If you save to your computer, if you want to save your parameters, you can save them. So what you do is you go here, screen. This is called the buffer area. Screen to buffer. And I clicked on that, and it brought all the parameters, these parameters over here. And then I would go File, Save Settings, give it a name. We'll just call it something here. Save. Oh, IRO error. I have to check what that is. So anyway, this is a prototype program I'm working on. So, and then let's say you loaded a file, they would go into the buffer, and then when you did that, when they were in the buffer, they're not on the screen yet. You can go buffer to screen, and it drops all those parameters over into the screen. So what this is a temporary save buffer, and it allows you to put parameters in here before you save them to your disk. I'm going to start the exerciser again. Actually, if I hit, it's far away on the counts here, so if I hit enable drive, it clears it. Whenever you hit enable drive, it clears all the counters inside the drive. Now, inside the drive, you have basically two counters. You have your encoder counter and your step counter. So when you hit enable drive, every time you do it, it clears them. Okay. So here we've got just the error signal. Okay, that's just your error signal. An error is you subtract these two, and that's what you get the error. Okay. Now your error is never going to be 0. It's going to be a low number, but keep in mind that these numbers you see here are 4 times multiplied off your encoder. So if you were using a 1,000-line encoder, all the numbers you see on the screen here to have to do with position are actually 4,000, because internally in the drive it multiplies by 4. So when you see it has an error, let's say I have a 1,000-line encoder on this, and you see an error of 4. That's not 4 of the 1,000, that's 4 of the 4,000. So that's really 1 of the 1,000. So okay, so what it's displaying here is the 4 times multiplier of your encoder. So it's not as bad as it seems. All right, so let me start. Okay, so this one here is just showing the error. This one is showing encoder in the step. So this is the most useful one. This one is the error in the step. So it's showing like it's showing where the blue is where it's supposed to be. That's where the step is telling it to be, and this is the error that it's trying to correct on. And then this one's the current, but actually I might have the current now. See if the current here. That's the current here. Yeah. All right. And that's the end of that for now. So if you have any questions, you can always call me or email me at larkin@storm.ca, and I'll be willing to help you with your problem.